All right, so welcome to today's class. I have just opened our syllabus that we were working through over the last weeks. So as you see, we've covered 1 and 2. We've covered week 4 completely. You've done a assignment, which is kind of a linear assignment on week 4. The week 3, we've covered maybe half of it, because SVM has 2 parameters, right? Cost and gamma. We covered the implication of what cost does in SVMs, but we can cover the impact and the implication of gamma in terms of the internal workings of SVM. And then week 4 is done. Week 5, we just got started on random forest a little bit, because last week we were having a more informal discussion about day-to-day lifestyle and working environment and different kinds of career prospects and different types of data scientists that people are looking for, and that usually exists, the type of type. So we're going to cover the rest of that as well. And then we're going to have a nice follow-up week. We're going to have a nice shift to a completely different technique, neural networks. These have got really popular these days, and especially with the whole buzz around deep learning, which is nothing but different, more complicated architectures of neural networks. So this is going to open doors for you to do some deep learning as well. Although deep learning is officially treated in the advanced course, the syllabus for the advanced course, but you can get started with neural networks and a little basics of deep learning. That's where we are. So let's get back to the SVMs. I started getting the assignments from the rest of you as well over yesterday and some today morning. So I will go through your code now since I have almost all the assignments. I'll check if I have everything, but I think I have everything. In terms of your cross-validation improvements and refinements. Any questions before we get started? Okay, so let's go ahead and get started with SVMs. So I'm doing a quick review of what we went through so that you're still connected with it. The SVM is trying to find a hyperplane that separates your classes, right? So it's like a linear, in terms of linear SVM. And that is formally posed as this problem, where you want to have the separation between these hyperplanes as high as possible. Yeah.
Can you share your screen?
Oh, yes. Let me do that. My bad. Yes. Okay. You should be able to see my screen. So yeah, so the class is about finishing the rest of SVM internals. So as a quick recap, but it's going to be a quick recap to what we already covered in SVM. We were looking at, you can see my screen, right? Yes.
Yeah, we can.
Yeah. So we're looking at how the separation between the two classes can be done in terms of linear SVMs, linear support vector machines, using these linear lines or hyperplanes if you have more than 2D data. If your points were described with more than 2D variables, then you're having a linear hyperplane. So there's many kinds of hyperplanes that you can use, but what SVM is formally trying to find is the hyperplane, the set of hyperplanes such that the gap between them, known as the margin, is as maximum as possible. So you're trying to maximize your margin so that you have a more clear, distinct separation between the two classes as much as you can generate in terms of the hyperplanes. So that is how the problem was formalized, and SVM solves for that. So we're trying to maximize the margin. So this is all we covered last week. Now what we're going into is, we also covered the concept of slack variables, where to account for increasing the complexity or decreasing the complexity of your SVM separation using, depending on whether you're overfitting or underfitting, you're able to do that by adding slack variables, which allows for little error. So if you had some slack, a black which was supposed to be on this side ended up here, and a white was supposed to be this side ended up here. So it's allowing for a little bit so that you're not fitting exactly through the data and memorizing it, because you might be overfitting them. So based on class validation, if you're required to underfit based on class validation, the slack variable allows for that, and making few errors a little bit. That was that was the concepts that we covered. Now the cost variable is basically allowing for how much slack you can allow for. So that's the cost variable, because you have in SVMs, as you work through your assignment, the cost and gamma. You're trying to maximize the margin while making sure you know how much cost you are willing to give in terms of the slack that you're allowing for. So if you need to allow for more slack, which means kind of reduce the complexity of your fit, because you don't want to overfit, then you want to have a bigger slack. If you want to increase your complexity, you want to allow for only smaller slack. So that's your cost variable. So parameter C can be, like I wrote here, parameter C can be viewed as a way to control overfitting. It trades off the relative importance of maximizing the margin and fitting the training data. So it's not only about just maximizing the margin when you're finding the hyperplanes, but also you want to make sure you're not overfitting, so underfitting. So you can control for that using the cost variable. That's why you're cross-validating to figure out what is the optimal cost that will give you the best cross-validation error, that you're not overfitting or underfitting, but you're optimally fitting. Now, as you remember in your assignment, you also used a variable called gamma. So we want to figure out what this is doing, right? Because in terms of the internals, to have some feeling for what that is doing. So this is where we move from linear SVMs to nonlinear SVMs. So the example we gave initially in the first few slides, we were able to draw lines that were separating the data, just through linear lines that were able to separate the data. So we were looking at linear SVM and linear hyperplanes, or linear planes. That is good enough if your data was linearly separable, right? Here, if this is only 1D data, it's not even 2D data, you have two classes, but these are clearly linearly separable, right? You can come up with a max margin by putting one line here and one line here, for example. But the question is, the issue is, in reality, not everything in terms of classification problems are linearly separable. So something like this is not linearly separable, right? If you put a line here, you're making two mistakes already. You're making 1, 2, 3 mistakes already in terms of the greens. But if you put a line here, you're making mistakes in terms of black as 1 black and 3 greens. If you put a line here, you're making a mistake in terms of 1 black and 2 greens. So how can you put a curve that somehow just makes sure that in terms of your classification map, blacks are always classified correctly and greens are always classified this side. So a linear separation would not do that. So that's why we go into nonlinear SVM. So there's nothing you can do in the original data set if you want to do with the linear SVM. So what nonlinear SVM does is it transforms your original data set into a newer space of variables, where in that space you would be able to have a linear separator be able to separate red and green. So that's what's being showed in this cartoon. So you take your original data, you apply another function phi on your original data x. So you go from original data x into phi of x, which is the result of applying phi on x. So you get this newer space where you can then apply a linear SVM. So here you see this is a linear plane. It's not a nonlinear curve. It's not a nonlinear surface. So if you can have the right phi that transforms it in a way that the data is linearly separable, then you can apply the linear SVM, like as if it was your original data set. You consider this as the original data set instead of this, because here you cannot draw one line and separate red from all black from green, right? If I drew a line like this, there's so many mistakes I'm making. Wherever I draw a line, I'm not able to separate it properly. But here it's like 100% separation. So that's the point of nonlinear SVMs, and phi is a nonlinear function, obviously, in terms of getting this transformation. So we need to figure out how phi needs to be defined, or how phi is implemented and stuff. Any questions at this point? Okay, so let's keep jumping into the next part. So now the question is about phi, right? And this is where actually your gamma is coming into play. I will show you some definitions of phi as we go ahead in terms of these slides. You will see that phi is not only a function of your data set, but it's also a function of a parameter, which is your gamma, or or it could be 1 by gamma. But in the end, it's a function of your gamma. So your choice of gamma decides how good or how weak your phi is. So it is also another way to control for overfitting and underfitting. Okay, because if you overfit, maybe you're using too strong a phi that makes sure you always get 100% accuracy in your training data, but on your test data, you might be having a having a bad accuracy, low accuracy. So you want to be able to not do this perfectly, but allow for little slack in terms of converting from this space to this linearly separable space where you can separate the classes. So that control is given by gamma. Now, there is something called the kernel trick. Now, SVM is known as a kernel method. For example, deep learning is a neural network-based method. Random forest is a decision tree-based method. So the SVM falls under a family of methods called kernel methods. There's a reason to that terminology, which we're going to be going into. It's kind of more mathematical, but we'll get to it, at least to be able to introduce you to the overall area here. So if you see the problem definition for the linear SVM, you can see that in the end, your objective function is something like this. You need to find some alphas for your data, which is your final solution. But your objective function you're trying to maximize, which is the margin, has this term called xi transpose xj. So this is what you want to maximize. And there are some constraints on your alpha that, a linear combination of this should be 0. Your alpha should always be between 0 and 0. These are constraints, but the objective function that you're optimizing, that you're maximizing is this. And if you see, it clearly has this xi transpose x. So what is your data set doing in terms of the objective function? Because alphas are the unknown, y's are your labels. So a data set is playing a role in terms of y here, but it is also playing a role in terms of the xi transpose x. So this is nothing but an inner product when you have two vectors, two columns, I and j. Xi transpose xj in vector algebra or linear algebra is known as an inner product. Now, in linear SVM, you're not doing anything to this inner product. But in nonlinear SVM, you're applying a phi on this inner product, actually. That is how you're getting a linear separation, as we will see in the future. So kernel, so we can, in linear SVM, we can call this in terms of terminology as this is our kernel. It's a linear kernel. It does nothing. The only kernel that you're using in your objective is you take your data set and you put xi transpose xj, and then you solve this problem in terms of maximizing for the alphas. But in nonlinear SVM, your k is not just directly the inner product. It's a function of your xi transpose times function of xj, because we said we want to transform your original data using a phi so that the problem is more linearly separable with a linear separator, like a linear hyperplane. So if you transform the data, what's going to happen? Instead of x, you're going to have phi of x, and instead of xj, you're going to have phi of xj. So then, in terms of x transpose xj, you would have phi of x transpose times phi of xj. That's what you have here. Now, this function is known as the kernel function. Now, what is the definition of phi you could use? So people have come up with different possibilities of phi. So one could be a function of this kind, where you're using square roots and products and squares, different powers. Or you could use a phi that looks like this. So this is another example of kernel function. So linear is not doing anything. So phi is nothing. So phi of x is x itself. So you have the xi transpose xj in terms of a kernel. In a polynomial kernel, you're doing this mapping where you're doing 1 plus xi transpose xj power some degree, power value. So there is a radial basis function kernel is another kernel where instead of using original data xi xj, which gives you the kernel xi transpose xj, you want to use phi of xi transpose phi of xj, right? And that function can be defined using this, for example, e power negative square of Euclidean distance. So distance between any two data points divided by 2 sigma square. This sigma is your gamma, actually. Okay, so in some places they use gamma, for some places they use sigma. It's just notation, symbol is symbol, but this is the role that your sigma is playing. So when you choose a gamma and cost, I told you about cost is deciding how much of slack you're allowing for to control the optimality of your fit from underfitting to overfitting, the complexity of your fit. And in terms of gamma, this is deciding how complex your kernel is. Because if you see, this is a negative exponential function. An exponential function is something that increases, but if it is a negative, it's something that decreases very quickly. So if your sigma was very big, then this distance divided by a very big number is going to be closer to 0. So it means it's decreasing slowly. It's going to 1. But if sigma was very small, you're going to have a very big number here. So negative exponential of a very big number means it is decreasing very quickly. So what sigma is influencing is with respect to any two given points, xi and xj, you have many pairs of points in your data set. It is telling how much the relation between any point I and its neighbors need to be taken into consideration. So is xi dependent only on one nearest neighbor in terms of its distance, like its closest other point, most similar point? Is it dependent on other similar records in your data set or other samples that are not just the closest single sample, but maybe they're the next closest 5 samples? So it is deciding how many neighbors of your data set you're using to store some information about any given point xi and xj. So it is controlling for, in a way, it is, if you're using too many neighbors, then you're trying to go for overfitting, or like for using more complexity of your fit. If you're using few neighbors, in terms of this distance relationship with respect to the neighbors, then you're using more simpler complexities of fits in terms of your SVM. So that's how your gamma is controlling for the complexity. So now your problem in nonlinear SVM looks very similar to linear SVM, except for that in linear you had xi transpose xj here, but now you have phi of xi transpose phi of xj. Now any function that can be written as phi of xi transpose phi of xj is known as a kernel function, and mathematically if this function is so we can get into the semi-positive definite stuff later, because I need to give you a linear algebra primer for you to be able to understand what that is. But basically it says if you computed the eigenvalues of this matrix K, and if all the eigenvalues are greater than 0, then it's greater than equal to 0, then it's a semi-positive definite symmetric. But I don't want to complicate with all this abstractness of math here, so I want to only stick to the overall mechanics. So you're seeing in linear SVM you had this, but the thing is it may not be able to separate non-linearly separable data, so you want to transform your data using phi of x. As soon as you would use phi of x, a function on your data, to get linearly separable separators, the thing is your linear SVM function, your objective function of SVM changes from xi transpose xj in this part to phi of xi transpose phi of xj, which can be called as the kernel function, which is what we're using in terms of terminology. Now, what is that function phi that you want to explicitly use so that you get some kernel? So this is an example for it. Okay. So your solution becomes like this in nonlinear SVM. You have a k of xi xj here, which is decided by your choice of gamma or sigma in these slides. So now everything else stays the same. Use the same optimization technique for finding alphas, which decide your hyperplane. So it's the same as linear SVM in terms of optimization, only your data is transformed using the kernel function. And that is how your gamma plays a role. Any questions here? We finished the other half of SVM that we'll put aside, and we can move to other topics. Any questions on your assignment or generic questions or the course material I just covered in terms of the gamma implications in SVM? Feel free to ask any questions if you have, and be happy to question things on why it is the way it is and stuff. Feel informal about this stuff. Any questions here anymore?
Rami?
Yeah. Go ahead.
So, what if it's so different, like if you get the same error for two different cost and gamma pairs, how do you choose which one is the best cost and best gamma?
So what are the cost and gamma, were the differences in cost and gamma little, or was the cost and gamma very different? Like the cost before to cost after versus gamma before to gamma after, were they very different or very similar when you got similar errors?
It's not very different, but they're close. But then I got same error for two different
I see the voice is chopping off. Is it just for me or for other people as well? It's kind of chopping off, but I heard partly of what you said.
Yeah, I couldn't hear it either.
Yeah, can you repeat it? Let's see if it improved a little bit. Or if not, I can give you the answer for it. Hello, Thiru, are you here? Are you able to listen?
Yes, I couldn't hear anything.
Okay, yeah, it really chopped off. Like the last part of what you were saying in terms of the differences between cost and gamma, it kind of chopped off. Can you repeat it again? We're able to hear you now.
Okay. So I was just asking if you get same CV error for two different cost and gamma, how do you choose it? I didn't have a very much different, like it's not a big difference of what cost and gamma that I have, but I just wanted to ask you if we really have a big difference, how do you choose?
Yes. So yeah. Okay. Yeah. Good point. So yeah, if you had small difference between so if you change cost a little bit and gamma a little bit, and if your cross-validation error stayed the same, there's nothing to be surprised about. So it's fine at that point, right? Not further investigation is required. It basically is saying you can use whatever cost and gamma out of those as long as you're okay with that minor difference in the error. But if you had, say, cost equal to 5 and gamma equal to 10, giving you a given amount of error, and then if you used a completely different cost and gamma, say cost equal to 500 and gamma equal to 0 or gamma equal to 1, which is a very different cost and gamma, and if you still got the same error, then there's not much we can do about it, but it tells us something about the data set. It tells us that the objective function that you're optimizing, the maximizing the margin, is a very nonlinear function because you're having different local minima to your optimal function, your function that you're trying to optimize. So it basically tells us that your objective function is minima of is having a minima at two different points, and those minima are exactly the same. So it will tell you that maybe there is some other cost in gamma that is very completely different that will give you a minima that maybe is even more lower than what you currently have. So it makes your problem of searching for an optimal cost in gamma a little more difficult because it is not, there is no trend in terms of where that minima is there. That will give you the least cross-validation error. In terms of practicalities, which is in terms of what do we do if we have this, all you can do is you chose, say, 100 combinations you tried or 10 combinations, and if you get minima error for multiple combinations, you can choose whatever combination there you want because there's no other information we have at that standpoint. So you just randomly choose whatever cost and gamma gave you the minimal combination. You pick one out of those two and go with it and implement it. But if you want to do more further investigations, we can do things like, hey, if I have two possible choices of cost and gamma giving me same error. Let me examine and try to find which one is better. So you can pick one cost and gamma and then apply in your test data set and see which one is consistently giving you lesser error. Instead of one time, in the future, you'll be monitoring your program or your product, and you'll be saying, hey, I'm running both. One I'm running in production, one I'm running in shadow mode, and I see the shadow mode is kind of more consistent. So maybe let me flip the production cost gamma with the shadow mode cost and gamma. So you want to see which one is giving you better consistent results or less variable. But it tells us a lot about mathematically about the objective function, that one is more easier to optimize, but if you have multiple minimas, it's kind of maybe a harder problem that you're trying in terms of finding the optimal cost and gamma. Practically, I would ignore it. There'll be a one-line answer. I would just use one. I'd pick whatever and then go ahead with it.
Okay, thank you, Pranay.
Sure. Okay, so
Praneeth?
Yeah, go ahead. This is a good time before we pivot into another topic. So go ahead with questions. Yeah, Manjeet.
Yeah, I have the same type of question. So what happened to me is like I'm getting same gamma values, 3 of them, 0.5, 0.5, 0.5, but the cost value differs, like 10, 100, and 1,000, but the CV error stays the same, and that's the minimum CV error out of 100 values.
Oh, you tried total 100 combinations?
No, I tried this 5 and 4, yeah. 20
combinations, I guess. 5 cost.
Yes, yeah. Out of 5 iterations, we get like 20 to 500 possibilities. CV errors out of it. The least errors are like I got 3 same values.
Okay, yeah. So let me draw a picture at this point because I told to some extent to Thiru. Let me share another angle to what is going on. This may be a little practical. It depends how to look at it. Let me tell you first. So you can see my screen the drawing board that I'm using. So what is happening is, say this was cost variable, this is gamma, right? Now, you didn't search all possible costs from 0 to infinity, and you cannot search everything possible from 0 to gamma, right? That is impossible right now. If you want to do it discretely, because there are like infinite combinations you need to try. So what you did is you chose some costs. Is that correct? And then you chose some gammas.
Yes.
Right. So and then you tried your luck at those places, right? Because in the ideally your goal is to find one cost and one gamma combination, which will give you the least error. That's what you did in your experiment. So say at this cost and gamma, I'm drawing a more cartoonish representation. Things will be a little more complicated, but this will make the point though. Say at this cost and gamma, your error was here, for example, and then your error decreased like this, and then say it increased, and then so you found the minimal error here, right? So say cost equal to this value, and then gamma equal to this value gave the least cross-validation error out of what you tried. But what you tried really was only this point, some combinations of points you tried. You didn't try everything. Right. So in reality, all you know is only how the error is at these points, but you don't know. Maybe in reality inside there is very complicated stuff going on. How the function is behaving. Maybe it's not literally going down. Okay? So this is one thing to be aware of. So maybe in here, you found minimum here, but maybe the true minimum is not here, but maybe the true minimum, if you searched everywhere in the middle of these two combinations, which you did not search, maybe if it's very complicated, you would get a very low minimum here. Maybe this is how the function was if you searched more points in this resolution. You see my point?
Yes. Yeah.
So all you have is the luck that you tried, and out of that, what is the best decision you can take? Now, what might have happened is the behavior in here. So now this is called a local minima. This is a global minima of the entire function. But you might have some local minimas here. So maybe the function came here and then it went like this and then it went again low like this. And this is a local minima. So it seems minima locally at this resolution. But if you look more carefully, there is a better minima, global minima here. This is the concept of local and global. Now what happened when you're getting same values is you only tried these 4 combinations, for example. And say you tried another combination here as well, this cost and this gamma. And there also you say you got the same value, right? Because this is same error, this is also same low. So it tells us there is some sort of flatness going on here, or maybe something like this happened. Then things went up again, things went down here. So you don't know until you try everything, which you cannot try anyway. So all you can try is you can again search around this and see if things are staying constant or not. So only thing you can practically do based on this, the story out of understanding this behavior of what could be the reality is the follows. So now the only thing you can do is you start with what you started with based on your resources, some cost and gamma. If you search more combinations, well and good in the starting. But at some limit, there's a limit to how many you can search. And then you find some minima at some particular cost and gamma. Maybe at this cost and this gamma, you found a minima. The rest of the points were higher, for example. Right? So your minimum was at this particular cost and gamma. All you can do is you can search around this. You can see, hey, let me put up this cost a little more. Say this was 5 where you found the minima, and say you found minima at 2 here. So then you will say, let me search little around 2. Let me search 2.5, 1.5. Let me search 5.5, 4.5. Let me try 5.75. And if things are again drastically decreasing, then it means you are close to the minima, but it's not the best local minima. Maybe there is a local minima even lesser, very close by. But if things are not changing,
trial and error.
Yes, it is a trial and error. Yeah. So it's an iterative thing. You try first, then you try around your best little more to see if things are improving a lot. Because you might have been here, and if things are improving just with a small change of cost on gamma, the derivative is high, so things are changing a lot more, or just slight change, then it is worth searching more. But if things are with slight change, things are not changing much, then you're maybe in this kind of a spot like this. You're stuck there. So however you try, you will always be in here only. Your error won't reduce much. So you try a couple times. You do first pass, which you did, then you try second pass of refining around it. If things don't change much, you stop at the second pass. If it's giving you a lot of reward, which is reducing error a lot more, then you try 3-4 passes. After a while, you're done with your time. You have a headache, right? You cannot do this forever. So then you're like, okay, this is the best I can do for now. This is a discrete world. So this is computers anyway. So you're working in discrete data. So we cannot search every cost. Then you say, okay, I will settle with this. Or if you have a requirement that your company is pushing you, keep on improving it. And if you find there is room for improvement with refining, you can further refine it. But if you know it is converged somewhere, it's not improving anymore, then you know there's no point searching forever because you'll always be staying there. So that's what happened. So you might have found costs and gammas of that sort. either if the cost and gammas are similar, then
yes, so we are plotting this errors against that.
Yes, exactly that. You want to plot your parameter against the error. Or you want to at least just view it with your eyes. You put it in an Excel sheet and view the parameter. And you see some trend, how it is looking. And based on that, you know where.
Sorry, Pranit.
Yeah.
Plating training set, not the testing set.
You always do this on the cross-validation. Whenever you refine it, you again cross-validate and see if your cross-validation is improving or not.
All right.
Yeah.
So this is what is done by the tune method in R, Pranit.
Yes.
So it actually does all the trial and error and gives us the best cost in gamma.
No, all that it is doing is not the trial and error. The trial and errors, even if you use tune, you have to do it. The only thing it will do is, for your initial set of cost and gamma that you're searching for, it will tell you which combination has the least error. But then you have to think about it, right? Then you will say, okay, maybe I will zoom around this cost and gamma. So you can change your search range a little more. So there is this range of parameters you feed into tune in SVM, remember.
Hey, Pranit, is there any way that we can choose this first cost and gammas that we are passing for trial and error, like, or is it done truly randomly, like?
It is not random. So let me say this. Let me open a small text document. Okay. Now I'm only giving you the practical know-how. This is the recommended thing. The very first pass for your data set, you know where the optimal cost and gamma is, correct? So I can tell you that you have to search in a very wide range of cost and gamma. You obviously cannot try infinite values. So give me pause for a second. Can you mute your computer? It's really noisy. I'm not sure if you're available. Okay, I think so too. Hey, can you mute your computer? Yeah. All right. I think this is very noisy. Yeah. Okay. Hemant muted the computer. That's good. All right. So, okay. So initially you have no clue. So you have to have a very wide search space. Now, obviously you cannot search infinite values. So what people do is do this. So you search values, say, let me write it down, then I will explain. It will make perfect sense. You try exponential -3, -2, -1, 1, 2, 3, 4. And say this. So this is an array of numbers, right? So C is giving you the array and then you're doing e power of that. So basically e power -3 is a very small value, okay? E power -2 is small value but little bigger than this. E power -1 still small value because this is 1 by e, this is 1 by e square, this is 1 by e cube. E power 0 is exactly equal to 1. Okay, then so you're basically trying very small values until 1 and then you're trying bigger values. E power 1 is about 2.2. E power 2 is bigger. E power 3, E power 4 is exploding quicker, you know, like 16, 64, 128, 256, something like that. So you try like this. You're at least catching a very wide space of very small to very big, very quickly. You can obviously use more numbers here and more numbers in this end as well. You can do 5, 6. So then you're looking even bigger values and even smaller values. Then this is your first pass. You pass this either through the code you wrote in your assignment, if you think it is perfectly written, or you pass it into the tune function in SVM, in R, right? Which is easier probably. Then you get your first pass of const star and gamma star, which is what the tune function or your function will tell you. Out of these possible combinations, so you have here 4 and 8, 8 times 8, 64 combinations it tried inside tune or inside your algorithm, inside your function. It gave you one cost and gamma, that is the least severe. If you have multiple cost and gamma, pick one, it's okay. Now what you do is, say this multiple cost and gamma happened to be, say it ended up becoming -2 for cost and gamma star equal to 4. Now the question is, you will see how the trend has been from -3 to -2 when you tried cost of -3, -2 and -1. Has things drastically dropped. So say -3 error was 100 and -2 error was 0.1. So it's like great improvement in error reduction. Same thing, if things drastically dropped, then you never know. Maybe you want to search if the minimum is somewhere between -2 and -1 or between -2 and -3. It gives you more room in searching. But if things were not dropping much, if at -3 error was 100 -2, the error was 99. -1, the error was 101. So it doesn't matter much, right? You're getting 1 point difference in error. So even if you search -3.5, -2.5, unless function is very non-continuous and some crazy things are happening, you will not have much difference in error. Your error may change from 99 to 89.9, well, 98.9 or something. So no problem, no worth in searching more unless you really need to optimize too much. So that is what you will know from in terms of the trend of your plot of what you initially searched, how things are changing with the neighborhood of your optimal cost gamma. So you want to search around the neighborhood. And gamma star, another story. Say your error, as you keep increasing gamma, your error kept on decreasing. And that's why out of what you tried, your maximum you tried was 4. But say the error was 50 here and here the error became 20. You don't know if you tried 5. Maybe there's a trend going on. If you tried just 5 in here or somewhere between 4 and 5 after that, maybe it will reduce even more. Have you reached the ultimate minima for a while, or is there more you can search? So depending on, again, if 3 to 4, if the reduction is very, very little, so it reduced from 100 to 99.9, then you can assume maybe 5 also, it will reduce 99.8, it won't reduce more. But then you will say, why, since it is reducing with every increase in 1, it is reducing only by 0.1. What I will do is, instead of searching 5, I will put maybe 10 in here. Maybe it will reduce a lot more, or maybe somewhere in the middle. So that will tell you how, at a what bigger increment or decrement of optimal cost in gamma in your first pass, you should be searching with respect to your second pass. So you do this 1 or 2 passes and then you're like, okay, this is the most I will do. Now I'm tired, but at least improved much better than my first pass. Maybe in your second pass, you figured out your optimal cost in gamma was -2.5 and gamma was 7, right? And then maybe your error reduced from 9.4, maybe from 4.6 to 1.6. So that's a big jump in error. So your prediction has improved a lot as your error reduced. So that is how you do in practicality. This is the thought process of practical tuning of machine learning parameters, not just for SVM, for neural networks, random forest, anything. Only your choice of parameters and definitions change, but this is how people search. First, you put a big net, and then you improve based on how the performance around the neighborhood of your optimal cost and gamma in your initial net has been. Any questions?
So the increases, the gamma increases, can we take it for granted?
There is no rule that error has to decrease when gamma increases. Maybe in this example it is happening for a while, but so you can search for a little while and then search. But if you put too much big of a gamma, at some point maybe your error is increasing again. So you don't want to take that for granted forever. You always want to search a little bit and then confirm.
As per the equation that you showed me a few minutes ago, like to the e power minus x of divided by 2 sigma square.
Oh yeah, that gamma, I see. Okay.
Yeah, so as per that equation, if we have a bigger gamma, the exponent e to the power of minus 0 is 1, right?
Yes. So what's happening here is, the intuition you can get is, practically speaking, if you're, by the way, one thing you need to know before I answer this is, some packages put gamma or sigma, whatever it is, in the numerator, in the denominator. Some packages will say 1 by sigma is equal to gamma, so your gamma will be up. So,
okay.
So then your understanding will get flipped around the other way around, right? So in this situation, if it was like this, implemented like this, then it will tell us that as your sigma is increasing, you're looking at lesser and lesser neighborhoods of each point. In influence of prediction of at one particular point is influenced by only few neighbors of that point. But if your sigma is very small, a lot of neighbors of any given record, so similar records are influencing the prediction at that particular record. So what that tells us is, if few people are influencing, it means you are trying to use less complexity of your fit. So you will know where your complexity is. If your sigma is increasing, if you are using more neighbors, which means you are using small sigma, then your complexity is higher. That's what you will know. But as soon as in some package your sigma is 1 by sigma is treated as gamma, means you have gamma above a numerator, which is equal to 1 by sigma. Then it is the other way around. Big will mean less complexity versus big complexity. That exactly flips around that logic. It all depends on how many neighbors are being used. Okay.
Okay. Okay.
Yeah.
Thanks.
Cool. Okay, so we covered SVM, cost gamma. You all have put in a good effort towards your assignments, which is definitely commendable, especially.
And Pranit, just a tiny doubt.
Yes.
So how big the CV error can be? Like, can it go to 1200 and as low as 0.1 or like that?
That's a great question. It is very relative to the data set you're looking at. So there is no universal big or small. So in some data sets, maybe a CV error of 300 is great, but in some data sets, 300 may be miserable. Depends on the data you're working on. So
yeah, the same housing data. When I spoke to Manish yesterday, he was telling the largest CV error he got is like about 100 or something. The same data set and the same procedure I did, I'm getting 700 of CV error.
By the way, I said if data changes, right? So if data is the same, as long as your code of evaluation and both the people's codes are, the right procedure of evaluation is being used, right? Because if you use only one correct evaluation, there is only one true evaluation, the God's evaluation of evaluating cross-validation error correctly, because some codes might have errors, right? If you use the exact correct way of measuring the CV error, if your data set is always bossed in housing, then the lower the better, obviously. So if one got 100 and one got 700, then 100 is doing better. So it means maybe the 100 guy has used better parameters in terms of that evaluation. Because since for you the code is also the same, right? The pack, if you're using the, say, code is also same. If you're using same R package tune function instead, and then one guy found a parameter where you have a lesser error on the same Boston housing, then that is a better prediction. That is, so maybe that person searched, or he was lucky in finding a better parameter of cost and gamma. So things won't change with the same data set if your evaluation code is same. So if things are happening differently, maybe one code is doing things better or both codes are doing things wrong, that kind of thing. Or maybe the one who got better error is evaluating wrongly. So maybe he's thinking he's getting better error, but his evaluation of computing the error may be wrong, right? So maybe that is also happening. So we don't know. That needs to be investigated.
Yeah, okay. So we have to mind only the least CV error, right, Pranit? Like,
your goal is to find the least CV error. To find the cost and gamma that gives you the least CV error.
okay, got it.
As long as your code is computing CV error correctly, you're using everything correctly, right? Because I can write a code, right? Just for cartoon's sake, right? I can write a code which does cheating and looks at the answer beforehand and it predicts only that answer. And then it will give some cost and gamma and say, okay, my answer is all, and but it will show since my whatever cost and gamma you give me, I'm giving 100% prediction. It means that my code has fault in it. It doesn't mean that my error is really low. So if things are evaluated correctly, then the lower the CV error, the better. But if the code has bugs in it and makes you believe that you're doing better than what it really is doing, then it's a different thing. So that's the extreme case. Okay, any other things on this point? Okay, great. So now since we finished SEM, I know we started random forest a little bit. So I would cover a little more of that before we go to neural networks in future classes. So let me close this slide, open this one. Okay, so this is a random forest. This is a completely different family of techniques like I told you last time. SVM kernel methods. Random forest is a decision tree method. You're always fitting a tree to do the classification. Literally like a tree data structure. Neural networks depending on another family. Okay, so let's go to the tree part. We've discussed a few concepts, some overall concepts of what ensembling means. It means if you have multiple classification methods, you can combine if you know a good way of combining the predictions or classifications of these individual methods in the right way, then maybe the weighted combination of your classification or prediction would do better than any individual classification. So maybe you have 5 kinds of SVMs, 10 kinds of neural networks, 20 kinds of random forest. Everyone will say this particular record is spam, this particular record is not spam, and some people will have some misjudgment. Some classification methods will say 10 methods may say this is spam, 20 methods may say it is not spam. So how do you use this majority vote of these expert learners? Some may be good learners, some may be dumb learners that they are predicting. So this combination problem is known as ensembling. in random forest, the idea of ensembling is used. You don't fit one tree. You fit 100 or 1,000 based on how many trees you choose. These are tuning parameters, just like cost and gamma. You give the algorithm to the random forest function in your package. I will show you later. You'll say how many trees you want to grow. So if you fit 100 trees will come with 100 judgments on every single record on what class it should belong to. Then somehow you will combine these. Do you average them to combine, get majority vote, or do you take majority vote and say you only take the vote that is believed by most trees out of 100? If 99% trees believes one thing, you probably believe that. So some way of combining, but this combination is done. That's why it is not called random trees technique. It is literally a bunch of trees that are used in the technique. So, in a nice way, he has called a bunch of trees as a forest. So it's called a random forest. Now, that is ensembling method. Now we want to figure out how these trees. So if you're growing 1,000 trees, at least we need to figure out how you draw one tree. So if you grow one tree correctly, then you can use the same function to grow 1,000 trees, or how many number of trees you want. So let's see how those trees are grown. Before that, this is the idea he's showing. You grow B number of trees and you average them up. Or you grow one tree on a subset of your columns. So if you had 1,000 features in your data set, 1,000 columns, each tree will grow on maybe 50 columns. But which 50 columns you will pick resampling. So each time a tree is grown on a different combination of columns. That is another way of doing bagging or bootstrap aggregation, which is ensembling. That is what is done. Brayman is a guy, is a professor from statistics department in UC Berkeley. He passed away in the 2000s, I guess. He developed the random forest technique. So he used this concept of bootstrap aggregation, which was developed separately, but as part of the tree generation process. So basically, he trained many trees on bootstrap data. This is the idea there. Now let's see how each individual tree is grown. So you bootstrap, when you say a bootstrap data set, it means a subsample of your data set, which is resampled. Resampling means sampling with replacement. So whatever you're getting might come again and again. So you're trying to follow the distribution of your data when you're doing the resampling. So you grow a tree. So let's call one particular resampled instance of the data set called Z star. You do this again and again because you want to resample B times. But again, now the question is, even for one resampled subsample of the data set, how do I grow a tree? If you know how to grow one single tree correctly to do the classification, then we can think about doing the same thing however number of times on however number of subsamples. So, and then the output of the algorithm skeleton is you do these trees and you average the predictions of all the trees that you grew in regression situation. In classification, you take a majority vote. So the majority number of trees, whatever they believe, that will be your final classification label that you're going to predict. Now there comes the final question. How do you grow a single tree? So the point is, in this structure in this cartoon here, each of these S0s, S1, S2, each of these is a different variable. So if you have 100 features, each of them is a different feature. First, you want to figure out, by the way, let me tell you something more fundamental. So this is, say, one tree that random forest grew. You will draw 1,000 trees like this, I said, right? What is going to happen is it will treat each node, it will treat it as a feature. It will have some condition here. Based on that condition, it will say how to split, which direction to go. Again, here you will know which direction to go based on the conditions being satisfied in your data set. So if your data set satisfies this condition at this variable and this condition at this variable, and then keeps on satisfying, and then end you reach some leaf till here, for example. Here in the end, you will have some result. If all these conditions are satisfied, then here you will only have label. It will say spam. Some things may say no spam, 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 no spam, no spam, no spam. So your email, if it's your training sample, test sample, when you're trying to predict, you pass through it. You have email has say 100 features. First, you want to choose based on S0 feature that the tree thought of using. Apply on that email wherever it ends up after satisfying all conditions. Every email has to end up in some leaf in the end. That is how the tree. It cannot get stopped. It cannot get stuck in the middle. It's not like some traffic, literally like on the vehicle, right? So there is a starting point, has to be the node, the root, and the end point has to be the leaf. So whatever goes in has to come out at end up in some leaf. In the leaf, you'll have the label spam or no spam. That is what you will use as a prediction for this tree. Now you will use 1,000 trees. The same email you pass into 1,000 trees, maybe 500 trees, maybe 700 trees think it is spam and end up in some label that think it is spam, and 300 trees end up in some label for the same email based on all these conditions that end up in no spam. So 700 is bigger than 300, so the majority vote wins. So you will say 700 trees thought it is spam, so we will predict for that particular email as it being spam. Any questions? Okay, so you do that. Now the question is, yeah, go ahead.
Quick.
Go ahead.
For all those 700 trees or how many ever trees that we are building, the root node is the same, right? We will have all the data because we are bootstrapping.
We are bootstrapping on the columns actually. So we are only using, the columns will change actually. So the variables will be somewhat different. Some commonalities will be there at some points, but they will change. Because if you have, of course you have maybe 100,000 emails, but 1,000 variables you're collecting for each email, your features.
Right.
Housing data, you had 13 variables. Those variables, in bootstrapping, if you had 1,000 to start with in your original data, say if your bootstrap size was say 100, each time you're only using 100 variables out of those 1,000. So you're resampling which 100 variables to choose. And out of those 100 variables, then based on one algorithm we'll go through now, in the next step, it will say which out of these 100 variables should be the root node. Because am I supposed to split on the variable number 99 first or variable number 3 first? Which variable should be taking the first decision will be chosen by the algorithm.
Okay.
Each tree has a difference in what subset it is using and also what subset it starts growing the tree from, based on a guided procedure we will go through. Yeah.
So the conditions will differ for each tree, like how they are divided.
Yeah, individually, only thing common is they have a tree structure and they're using some set of variables from this data set, but variables are changing, initial conditions might change. If some variable is very important, it might happen out of 1,000 trees, a majority of the trees will use the same variable automatically as because of the algorithm, because that is the first variable to split on. Because maybe that variable, if you split on, is the most easiest variable to split on to separate your two classes as much as possible. Then you will use the next best variable like that. The idea is to do greedy stuff. So it's a greedy algorithm. First you use the best, figure out which first variable you need to use given a subset of variables for any given tree. Best variable that will give you the best split is what you use first. Next greediest best, next best possible, use next like that. Just keep going lower and lower, you're making very fine decisions. So here I'm saying if gender is male, and if education is like this, and if payment is like this, then then he's likely to be a good performer in paying the credit card bills. If gender is male and if the education like this, something like this, family size like this, then he might end up in a load saying, hey, he might be a very big loan defaulter. You should be very careful in terms of what you do with the credit card company and what decisions and what credit limit you give them and everything. So yeah. All right. So question now, how to split? You're zooming in as you see, right? We came up from this idea till here, but we still didn't figure out. Now what is left out is what is the criteria to make the split for any given variable, or to choose which variable to split on and then how to split it. So here what is the time by the way? Okay. So I will say a sentence or two and then we'll continue on this just like we continue on SVM next week. So the criteria used is known as information gain. It is a statistical concept. It's also used in an area called information theory. So basically this is the idea. You want to make sure at what threshold you want to say. So if it was a numerical variable, if this variable was greater than equal to some number or less than equal to what number it's supposed to be. So that based on that split you get two subsets, right? If it's less than, you have this number, greater than this number. What is the threshold supposed to be for any numerical variable? I will talk about categorical separately. So that false positives, false negatives, your classification rate is accuracy is higher, less false positives and less false negatives. Meaning what is supposed to be in class 1 and end up in class 2, or what is supposed to be in class, those are the false positives and false negatives. That has to be low and your accuracy has to be high. So what is supposed to be in class 1, if it did end up in class 1, was 2, that is the accuracy. So you measure that split, but you measure that the quality of the split using information gain. I will explain this very clearly on why this is a good measure in the next class. And then as you see, this few slides will explain why that is a good measure, and then you will see an example with some Simpsons cartoon example of how random forest is applying it. You will get the overall idea. Since you already know the idea of the structure of how this flow is happening till here, like we discussed. Now, once you understand about this measure, you will understand random forest very well, to an extent that you can explain in an interview on the board or something. Someone asks you tell me how random forest works. All right, any other questions? This is the end of the course time slide for now. Okay, yeah, go ahead. Yes, Very important. So your first project definitely needs to be a supervised learning project. So it needs to be regression or classification, which is what we've been learning and doing till now. So it's going to be an extension of your assignment. Ideally, if you all do not want to apply use just Boston housing as your project data set, that is perfectly fine, right? Why do we only use Boston housing as a data set? It has been a good assignment data set. So ideally, if you can use the UCI machine learning repository, UCI ML repository, if you search for that on Google, I just sent it on the chat window. I will send it an email as well. But if you search for that in Google, you will get a website with a lot of data sets you can choose from. Choose anything that says classification or regression, and then choose a data set that catches your mind. Do find 3 data sets that catch your mind in general, that you will be liking to work in. Just catch your mind in terms of you like that domain of work or something like that, right? And then we will apply SVM, random forest, and neural networks, and we can use that as one project or 2 projects, right? So you can say maybe SVM and random forest is project 1, neural networks is another project. So it will be some more of an extension of an assignment of using these tune functions in our using the same cross-validation methodology. So that way you will have an end-to-end report for a project of a few pages. So it's something to do. It's a to-do task. Is just in your free time, hover around that website and try to catch about 3 data sets. We're going to narrow down into 1 data set for each. So say Kamal catches 3 data sets, he likes Manideep 3, everyone 3, Thiru 3, Manish 3. So everyone, we will look at everyone's 3 data sets in next call, and we will choose 1 out of that as being a good data set for you for your project. Some things to keep in mind: if you have some amount of missing data in that data set, it's okay. There is a tab on the website that says for every data set before you download, incomplete data equal to yes or no. If it is yes, it is still okay. You will even learn in the project how to deal with incomplete data. But make sure that you have a data set that is not vastly incomplete, because sometimes real life data sets, out of 100% of records, maybe entries, maybe 99% or 90% is empty. That is not a good data set at all for a student who is learning in the beginning to apply machine learning, because then you are firefighting with how to deal with incomplete data. You're doing a project on that instead of doing a project on how to do machine learning after dealing with incomplete data. So make sure that is taken care of. And also don't choose a data set for your first project that has millions or hundreds of thousands of rows or columns. Neither should be very high. I'm not saying it is a bad idea to work with big data. I'm just saying it will make it harder for you to first implement the methodologies correctly. So make sure something is handleable in your laptop or your desktop that you're going to use for your project work. We will actually do a project which will deal with big data, definitely at least more than 100,000 records. That's a feature. For our second project, we will use a separate framework, at least something like Spark or H2O, but will be the next project. So let's stick with this. Any questions on that? Picking or choosing data set? Okay, so if you have any other questions during the process of choosing a data set, feel free to email me. Your project will be an extension of what you've been learning. So we are not doing a project where it's not like your 4th year degree project or something where you can do whatever you want and you don't know where to start from. Here, whatever you're learning, you're going to apply on this data set and pose it as a project. So random forest, SVM, neural networks, we will apply on this and use it as a project for your resume. All right, so let's call it a day. You have a good rest of the weekend. Let's see you next week again. Feel free to email me with questions if you have any. All right, see ya. Bye-bye.